Okay, in this video, what I hope to do is to make you feel a little more at ease when you're working out projectile motion problems, or for that matter, problems where you need kinematic equations. Okay? Let's start off by actually showing a problem and you seeing me work through the problem, and like I say, hopefully that will put you at ease when you're working out problems and at least give you more confidence when you're working problems out. And the problem that I'm working with here, the problem says a motorcycle stunt rider rides off a cliff, the edge of a cliff. Just at the edge, his velocity is measured to be 5.0 meters per second, and that velocity, if it's just before the bike leaves the cliff end, has to be in the x direction, so that's the velocity in the x direction. The cliff is 200 meters high above the ground of the valley below. Okay, so what I like to do when I start off problems is I like to write out the kinematic equations, and you may be familiar with there are 5 kinematic equations, and since this is a two-dimensional problem, remember it's a projectile motion problem, okay, we need to write those equations both in the x direction and we need to write them in the y direction. So what I've done is I've taken those basic kinematic equations and broken them both into an x direction and a y direction. In addition to that, what I've done is I've added a column here for what's missing from the kinematic equations. Okay, so if you look, for instance, at this very first row here, these two equations, we have the final velocity, the initial velocity, we have acceleration, we have time, final velocity, initial velocity, gravity, and time. And what's missing from that would be the direct, not the direction, but the distance, okay, in the x or in the y. Now the kinematic equations, pretty much they cover problems where you're dealing with velocity, distance, acceleration, and time. So of all of the of those variables that I just mentioned, distance is what's missing, or displacement, whichever way you want to look at the problem. Let's go ahead and use the term displacement in this case. Displacement is what is missing from the equation here. Okay, for this second set of equations here, you'll notice that the displacement is written here. We have initial velocity, we have time, and we have acceleration. What's missing from this equation is the final velocity. So you kind of get an idea as to what how this table is set up. Okay, so let's move this back here just so you can take a look for a little bit more. All right, so now that we've gotten that, I like to think of this as being my toolbox, by the way. Let's first look at what the problem gave us. Okay, so what the problem gave us, and I'll write this over here on a separate sheet of paper, is the problem told us that the rider's x direction, the initial x direction, is equal to 5.0 meters per second. Okay, what we can deduce from the problem, figure out, is that the y direction, the initial velocity, is equal to 0 meters per second, and that's because just before the rider leaves the cliff, the rider is not moving in the y direction, and so therefore the velocity in the y direction has to be equal to 0 meters per second. Okay, in terms of the initial in fact, let's just call this delta y in this case. In terms of our delta y, which is our distance from the bottom of the valley up to the top, and which would be the displacement that the rider would experience in the y direction as he comes off the cliffs and hits the floor there, or the ground below. Okay, that distance will be equal to 200 meters per second according to the problem, right? Pardon me, not 200 meters per second, but 200 meters. There we go. So let's erase that off of there. 200 meters. Okay. Okay, what else do we know? In terms of our initial displacement, let's move that a little bit there. We know that initial displacement in terms of the x-axis, that will be equal to 0 meters. Okay, And the reason that's equal to 0 meters is because we're thinking of the problem beginning just after the rider leaves the cliff. Okay. What else do we know? Well, we know that gravity, the magnitude of gravity, is equal to 9.8 meters per second squared. Okay. Is there anything else that we can pull from the problem? Well, yes, there is. The acceleration now in the x direction. Well, what happens is just after the rider leaves the cliff end, we're pretty sure that the rider won't experience any force in the in the x direction if we ignore, for instance, like air resistance. And which for this problem, let's go ahead and ignore air resistance. Okay. So once the rider leaves the edge of the cliff, there is no acceleration in the x direction, no deceleration. And so therefore then the rider will have a acceleration in the x direction of 0 meters per second squared. Now, having said that, what we can also say then is the rider's final velocity at any point we pick, okay, to be the final, all right, is going to be equal to 5.0 meters per second in terms of the x direction, right? Because the rider is not going to speed up or slow down in the x direction. Okay. So now, given that that's the case now with our givens, right? Let's go back and see what's the first thing the problem asks us to find. First thing the problem asks us to find is to find the rider's velocity in the y direction at 0.50 seconds. Okay. So given that that's the case, actually let's take a look at this. So we know what the that the rider, since this problem is moving in the y direction, we know that the rider's initial velocity, okay, in the y direction is 0. We do not know what the final velocity is, and that final velocity is at that specific instant in time, okay? Not when the rider hits the floor, but at that specific instant in time. We do not know what the final velocity is equal to. We know what gravity is equal to, and we know what the time is equal to because they want us to find that at 0.5 seconds. So therefore, this first equation here in the y direction, the first equation here would be a good equation to use in order to find that velocity. So let's go ahead and find that velocity then and rewrite the equation. We know that in the y direction at some given instant in time, so writing this as a function of time, is equal to, according to our equations, kinematic equations, Vyo plus gt. Well, we know that the initial velocity is equal to 0 in the y direction, and so therefore we have Vy of t, which is equal to gt. Okay, we know that g is equal to 9.8, or at least the magnitude of it is equal to 9.8 meters per second squared. And we know that time 0.50 seconds. And so we can calculate the velocity in the y direction at a specific instant in time. And let's go ahead and put 0.5 in here. At the specific instant in time, which is 0.50 seconds. Okay. And so what we would end up with is a velocity in the y direction, a velocity in the y direction at that instant in time to be equal to 4.9 meters per second. And of course, that's going to be heading downward. Okay. So that is the answer to the first problem there. All right. The second problem now asks us to find. They want us to find the velocity of, and we have an error here, find the velocity of the rider at 0.5 seconds, 0.50 seconds, okay? So the other one, we are finding the velocity in the y direction. And remember, we know what the velocity is in the x direction throughout the entire flight, okay? It's always going to be that 0.5 or 5.0 meters per second, okay? So because of that then, we may actually use, let's use this paper from over here. We may actually find the velocity of the rider, and that velocity would be equal to the square root of the following: v of x squared plus v of y squared, right? Okay, to find the magnitude. And when we take the square root of that, we know that, let's see, we know that in the x direction is 5.0 meters per second square. We know that in the x direction, or in the y direction, it's 4.9 meters per second square. And so when we calculate this out, okay, and I've already calculated it, you're going to end up with a velocity of 7.0 meters per second, okay? 7.0 meters per second. Now, we do not know the direction of that 7.0 meters per second, and that's what the third question wants us to find. They want us to find the angle of the biker at 0.5 seconds. Let's put a 0 in here. 0.50 seconds, okay? So let's go back to this paper over here, and I'll put it in this area right here. And you remember, if you want to find the angle, we can take the inverse tangent of the y over the x, and in this case is the velocity in the y direction over the velocity in the x direction at that 0.50 instant in time. And so then that's theta is equal to the inverse tangent of, and remember our y direction we found to be 4.9, right? And in the x direction, remember, we're saying that that's always going to be 5.0. Okay? And if we go ahead and calculate this out, what we end up with, and I've already done this, and I encourage you to actually calculate this out on your own calculator to make sure, we end up with a 44 degrees to be the angle. So that velocity, the driver at 0.50 seconds is moving 7 meters per second at an angle of 44 degrees below the positive x-axis, if you will. So let's suppose the biker is here coming off the end. That angle then would be below the x-axis here by 44 degrees. Okay? All right, so one more problem to work out. The question is here now, how long does it take the rider to hit the floor? Okay, how long does it take the rider to hit the floor? Well, we know what the final distance and the initial distance combined together. Pardon me, let's use the y direction. There we go. We know that these two together is equal to the 200 meters, right? Okay. We know that the initial velocity is going to be, or is equal to what? 0. We know what gravity is equal to. We know what time is equal to. So we can use this equation. This is the best one to use of them all. And you can go ahead and check to see if I'm actually telling the truth about that. All right. So given that that's the case, then I'm going to write y of f minus y of 0, which is equal to v0y of t plus half gt squared. Okay, and remember, we can write this as being just the change in y. We know that the initial velocity is equal to 0, and so therefore that term gets canceled out, leaving us with just half gt squared. Okay, and remember, we're trying to find the amount of time before the rider hits the floor, the bottom there. So we can manipulate this equation here so that it comes out to be equal to 2 of delta y divided by, and I'm just going to do this quickly here, which is equal to this, okay? And we can fill in our information. We have 2, the difference in height would be 200 divided by 9.8. Take the square root of that, and that's equal to t, and that leaves us with 6.4 seconds as the time. Okay? All right, so that was a little bit quick, but you can go back and review this a few times. So this is just how you would calculate this problem anyway, using the kinematic equations for a projectile motion problem. Please do check out my YouTube channel for additional tutorials on this sort of information. And also you can check out my website. Website is www.clydeletsum.com.